Yep. Okay. Well, thanks everyone. Great to start us off tonight at our members' night. And yeah, so I'm going to talk to you tonight about pretty much this question here, which broadly summarizes my master's research I've done this year, and really asking this question: can we trust what we see in the rock record? Is what we're seeing in the rocks actually preserving what we think we're seeing? So the title is Assessing the Sedimentary Record of Ocean Acidification Prior to the KPG Mass Extinction. And that is the shorthand for the infamous dinosaur killing mass extinction that occurred some 66 million years ago. And if you've been watching BBC recently, you might have came across the new David Attenborough documentary looking at a site in North America that preserves the very day, so it's said, that the dinosaurs went extinct. But I'm going to be looking at one of our most, pretty much one of the best records of this event. What we can see here is a nice deep sea core, 1262. And that boundary there, you can see the abrupt colour change from the pale sediment to the dark sediment marks the boundary. But for the premise of this talk, I'm going to be looking at just prior to the boundary and looking in a few sediment cores prior to that, and these question marks over what exactly are we seeing? Are we seeing ocean acidification or not? So next slide. Yeah, so we should, ocean acidification, the sedimentary record, what do we know? We owe a lot of what we know to these deep sea drilling legs. This is the JOIDES Resolution, riserless drill ship, part of the International Ocean Drilling Discovery Programme. It's a global consortium of geoscientists that get together, lots of funding, lots of money in these drill ships, and pretty much core different parts of the Earth's ocean depths. And sometimes we hit lucky, we come across these beautiful records here. This record here preserves a well-known event, a well-known abrupt climate change event called the Paleocene-Eocene thermal maximum. You might have heard that of before in terms of climate change. And what we're really seeing here is that traditionally, historically, sedimentary evidence really shows these events, these abrupt ocean acidification events really well. We can see to the right there, that blue record, the graph in blue, is a record of Earth's temperature some 67 to 52 million years ago. The last time we had a greenhouse kind of climate when it was warmer than today. We can see that overall, the record is punctuated by these abrupt spikes, I like to call them, these temperature transient warming events that they're called, or hypothermals, which are almost like the geological analogue of what we're currently in the process of doing today. But what we can see is there's a nice correlation between these blue spikes and increases in global temperature and these spikes in the purple graph below, which is iron intensity. We can actually see that very nicely here in this blown up image, that to the kind of black dotted graph to the right there is showing an increase in iron intensity at the onset of the event, and we see likewise a decrease in the blue graph, which as you can see is the weight percent of carbonate or limestone in the core. So what we're really seeing is this sedimentary kind of blueprint for these abrupt acidification events, rapid decreases in calcium carbonate and likewise rapid increases in iron intensity. So if we go to the next slide. So my master's by research project looked at one of these earliest events just prior to the Cretaceous Paleogene boundary, some 66 million years ago. And then what I've just done is I've blown up that section. Again, we're seeing the nice blue curve there. That's the warming event blown up. But what we're seeing here is that at the bottom here, the iron intensity is not like the others. We're not seeing this big peak mirroring the blue graph, the warming event. What we're actually seeing is this variable signal coming through. We've got these punctuated spikes of varying intensity throughout the event. So it's not really showing us what we traditionally expect to see in these deep sea sediment cores of these abrupt warming events. It doesn't seem to be characterized by the classic increase in iron intensity. And this has actually led some authors to suggest that maybe this particular event, this late Maastrichtian warming event, occurred 340, give or take, 1,000 years before that asteroid impact did not actually cause any ocean acidification. So if we go to the next slide as well. Another interesting thing, scratching our heads about this as well, is if we plot the sedimentation rates in the core during this event, we actually see the opposite. We see an increase in calcium carbonate and carbonate deposition. We see this big jump in sedimentation rates. And in these deep sea sediment cores, sedimentation is recording influx of marine snow. So that's like the phytoplankton living in the water column that produce calcium carbonate shells. So we actually see an increase. So this actually goes against the traditional thought in a lot of these earlier, later events. So what is exactly going on here? So we go to the next slide. So this event's quite interesting for a multitude of reasons, but its association with the Deccan Traps, perhaps its most famous kind of link. So it's surprising because this particular warming event, this 4 degrees rise in global temperature, is actually being correlated by some authors to the Deccan Traps. And for those of you that don't know what the Deccan Traps are, it's this large volume of flood basalt lavas that erupted in present-day India at this time. And for some time now, there's been arguments to suggest that particular warming events that we're seeing in this record are linked to these large basaltic emplacements. So if we go to the next slide, we can kind of show what how the authors came to that conclusion, most recently in 2017. So, for example, this warming event, it doesn't line up to what the Earth's orbit's doing. So the warming event actually occurs during a trough in what we call an eccentricity minimum. What that really is that every 405,000 years, the Earth's orbit around the sun brings the Earth closer or further away from the sun. And if the climate is at a sensitive state, we can actually induce a warming event, almost like our glacial interglacial cycles. Only we're doing the opposite. We're causing abrupt warming events instead of ice ages. However, this doesn't seem to line up. The peak, as you can see there, actually the blue graph actually starts in a minimum at the trough. If we go to the next slide as well, another interesting thing is that if we look at the red curve, which pretty much is a record of the carbon cycle, we can actually see that it's characterized by this unusual negative muted excursion, which we can see right here. We're not seeing an abrupt decline as we would expect to see in other events. It's quite, where you'd place the onset of the event looking at the red curves, actually quite hard. Is it starting here, or here, or here? It's not very clear. We're not seeing a very mirror, we should be likely seeing a nice mirror image to the blue curve, which we're not seeing. And some authors have suggested that muted signal is in fact due to a mantle source of CO2, heavier CO2 causing the carbon cycle to almost have a muted signal. Not if it was a light carbon source, carbon 12, we would see the delta 13 ratio show a very big drop, which we're not seeing. So we go to the next slide. So that begs the question, suggests that what is the iron intensity in the core, in the calcium carbonate, actually recording? And if we think about the sedimentology, there's varying different ideas of what they could mean. For example, iron intensity is not just showing potential a lack of carbonate. It could potentially be showing an influx of aeolian-blown dust. I should mention that this site, 1262, just lies off the coast of Namibia in the Anglo Basin. So potentially, are we seeing influxes of continental wind-blown dust? And some authors have actually suggested that this could, in some parts of this core, be an example or a reason of why we're seeing this iron intensity. So there's more than just one reason. Likewise, if we go to the next slide, we know that even in the present day, satellite images just off the south coast of England, there are large blooms of phytoplankton. These are coccolithophores, these minute nanofossils that make chalk. And these things bloom in under the right conditions. So potentially the calcium carbonate that we're seeing during a warming event might be due to, if we're getting this abrupt global warming event, perhaps we're getting more stratified, nutrient depleted surface oceans, which these sea bugs love and bloom in. And as a result, we have an increase in the calcium carbonate production in our core, which is counterintuitive of what we might think to be preserved. So there's multiple different ways of looking at this. We go to the next slide. So how do we solve this issue? How can we kind of pick through that and kind of understand, is there a signal for volcanism? Are we seeing ocean acidification, but is it preserved? So we need to turn to a different type of application, away from sedimentology for a moment and looking more at trace metal geochemistry. So my work really looked at using this particular proxy, a geochemical proxy, the boron calcium trace element proxy. What's really good about this proxy is it's been used by various authors to show evidence of ocean acidification in the geological past. And it works a wee bit like this. You can see that in the diagram to the right there, large volcanism, say the Deccan Traps, outgassing large quantities of CO2. As you'd expect, that CO2 would enter the atmosphere and then be absorbed by the oceans, the world's largest carbon sink. What we then would expect to see is, as that carbon dioxide has been absorbed by the ocean's pH or acidity would increase, or the pH would drop. Chemically, that would involve a decrease in something called borate ions, which is a chemical ion that you find in the water, in the seawater. And then this is a blown up image of one of these microfossils, a foram, benthic foram, and you can see that's 200. That's very small, by the way. That's not the life size. You're talking about things the size of a grain of sand. But these things living in the oceans at the time would then record a decrease in the boron to calcium ratio as they're growing their shells, precipitating their shells in that ancient seawater. So chemical changes in the oceans will be recorded in the shells of our microfossils. And likewise, if we go to the next slide, and again, I think, yeah, we see this thing, a chemical gradient in the ocean called the lysocline, shallow. And when this lysocline is just a chemical gradient which really shows the preservation of calcium carbonate limestone over clay, iron-rich sediment. And that would expect it to shallow. So we would see a decrease in the calcium carbonate and an increase in the iron. So we go to the next slide. Yep, so that led me to the hypothesis that if we implement this boron calcium trace element proxy, the record that we produce should show an ocean acidification event. We've got a warming, we've got a carbon cycle perturbation, potentially a link to Deccan volcanism and CO2 release. So this should hypothetically show this outgassing of the volcanism. So if we go to the next slide. So how did we get there? Well, we start off, next slide, with our core. So the core that we've been looking at, 1262, was actually recovered back in 2004 on one of those ocean drilling legs. It came from, I think it was like 3,000 meters water depth, so 3 kilometers down in the ocean. And they managed to bring up this beautiful core containing this kind of clay nanofossil ooze full of these microfossils that we were so desperate to get after. So we go to the next slide. So yeah, the samples were then taken and washed and prepared in various different processes there. And I found these samples as they were in the second picture there in these little vials, already cleaned by the scientists. But no one had ever actually went through the samples and performed these analyses on them. So we go to the next slide. Pretty much my master's for the first half of the year involved foram picking. So what that really involved is I'm taking these individual beakers, emptying these dust, sand-like sediment through a sieve, and then sieving that sieved material onto a picking tray, and with a microscope and a fine toothbrush, I'm going through and looking for the particular species of foram that I'm looking for that was a good archive for this particular technique. The final slide. We can go down and then, yeah, so after gathering those particular samples together that I was looking for, they were then crushed, cleaned and dissolved and ran on this fancy mass spectrometer here. This is the triple quad ICP-MS at the University of St Andrews. And that machine there was able to measure within those, we're talking about material the size of a grain of sand. So that machine was powerful enough to give us the chemical ratio of boron to calcium, which is a proxy for ocean acidification. So we go to the next slide. So yeah, this is the results here. This is what we're seeing. Interesting bit. So yeah, so global signal. Are we seeing decking outgassing? You're probably wondering, are we seeing this outgassing of the volcanoes? So the data here, we can actually see, does confirm a progressive decline in deep ocean pH and or potentially an increase in dissolved inorganic carbon, so just an influx of carbon into the deep ocean, occurring within the first 40,000 years of the onset of the event. So here we've got the muted signal. What do we see? We see the graphs falling in the quantity of boron to calcium, a negative boron to calcium excursion. So potentially that is the acidification signal. And then as the carbon starts to recover, starts to increase, we see an increase in the signal to recovery from that event. So potentially that there is the ocean acidification signal of the event. And we can constrain that very well because with the inconsistencies and the trouble trying to look at the red curve, we can really nicely see that nice drop in the middle of that graph there. We'll go to the next slide. And it's also shown nicely as well in our calcium carbonate. We're going back to our sediments. So the zigzag curve was the 1262 data, and that was very unusual because we're seeing an influx, we're seeing large variability. But if we look at other sites, at other water depths, at different sites at this time, we're also seeing the drop in our data set shown also in calcium carbonate from different cores as well. So you can imagine as this event starts, influx of CO2, increasing global temperatures, the ocean's absorbing that, ocean's acidifying, and as we'd expect calcium carbonate to decrease in our cores and then afterwards slowly recover. So we're seeing that very nicely as well. So we're just going to the next slide. Yeah. So what is causing the variability? So we've got the signal, but why is it so hard to see in this core? What's going on? So other authors have already looked at this before, looking at the sediments themselves. And we've been able to show that this spikiness in the iron intensity, for example, over the calcium carbonate is actually driven by precession. So that's another type of orbital change every 21,000 years. So small changes to the Earth's axis allows more solar insulation, more solar energy to come in and warm the planet. And if the climate is very sensitive, as it was back at this time, we are actually seeing transient ocean acidification events every 21,000 years. We're not seeing a big, massive one, but we're seeing this pulsated shallowing in acidification under the greenhouse conditions at the time. So we go to the next slide. And again, the variability within the data set, the new geochemical data set that I produced actually shows this very nicely. These iron spikes that we're seeing in the core correlate to these abrupt, if we look to the red core over the red graph, sorry, over the orange one, we're actually seeing a lot of variability, a lot of these kind of negative boron calcium excursions correlate nicely with these iron peaks. So what we're seeing there is declines in boron calcium, acidification, and therefore an increase in iron over calcium carbonate in our core. So yeah, again, not to complicate this further, but we actually think that this is due to enhanced productivity. So we're getting calcium carbonate being produced, but we're getting a lot of that productivity, those blooms of phytoplankton in the surface oceans. And they're going to bring down light carbon, carbon-12. And in fact, when they fall to the deep ocean, they're actually going to cause the deep ocean to become more acidic because they're bringing down lots of carbon with them. So in fact, these precession events that we're recording are in fact blooms, I believe, of these phytoplankton that are bringing down light carbon. And this is the climate system trying to modulate itself during this abrupt warming event. So we go to the final slide, I believe. So what's next? So why should we look at these events, for example? So if we compare these past events in the geological record, these hypothermals, to some of these future anthropogenic human-caused warming that we're expected to experience under different scenarios, it really highlights that there will be several possible long-term environmental consequences to the current climate crisis, depending on what we want to do if society continues to allow emissions to rise. We've got that first core, that event, the PETM, a rough, and you can see there, model there, sea surface temperature before and after the event, on average 5 degrees, a change of 5 degrees. And we can see what that done to the core and what that did. This here is one model for the year 2500, geologically a blink of the eye, a few generations away. But this particular model is in one which society chooses to go down a weak mitigation scenario, in which we continue what we're doing today and we don't really change. And we continue doing what we're doing for the next few centuries. And what are we seeing? We're recreating the PETM. We're not doing it at the end of this century, thank goodness, but we're just kicking the can down the road a few centuries away. Still a geological blink of the eye. So I'm actually fortunate enough to be continuing looking at this work, and will be the kind of focus of my new PhD research at the University of East Anglia starting this autumn, in which we're going to try and better constrain how much did the planet warm during these past events, and that will give us a better idea of how the climate system might potentially operate in the future under some scenarios. So I think that's us. So open the floor to any questions. Thanks.